This is Mr A Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. So I'm here to discuss on the topic steps involved in modeling fluid flow problem in computational aerodynamics. So before that, let's see, there are different approaches for the fluid flow problem. One is Eulerian, other one is Lagrangian. So let's see here the flow through a pipe. Okay, so or let's flow through a channel. So here you can see there are different fluid particles. Okay, so these are like the fluid particles. So let's say this is the cross section of the pipe. Here, when these fluid particles are entering, so with respect to cross section, what is the flow properties? Let's say, so what is the pressure? So what is the velocity? Okay, so these things, if you are calculating with respect to this cross section, let's say this is x direction and this is y direction. So if you are calculating the values of pressure with respect to function of y and velocity function of y, okay, along this cross section, so it's like you will be taking the average, so the average properties of the fluid flow. Fine. So this approach comes under the Eulerian. So basically, in the case of Eulerian method, uh, if you see the fluid, whatever it is there, it is moving through particular cross section. So you will take the average properties, flow properties of the fluid medium. So when this fluid is passing through one station, let's say this is station 1 to station 2, so it carries mass, it carries like momentum and energy. So when a fluid particle is moving from station, let's say this is the station, okay, from here to this station, okay, if it is going, so there will be mass, momentum and energy. Okay, so these changes will occur. Fine. So these equations will govern this fluid flow problem. So in the case of Eulerian approach, so if we are looking the average flow properties for a given cross section, so then that would constitute to the Eulerian method. Okay, and here you can see that in the case of Lagrangian approach, so you will track what is the behavior of a fluid particle. So here individual. So if you are concerned about the average of the flow, so if you take any small space, so you will have so many number of fluid particles. Okay, so if you take any average space, so you'll have so many number of fluid particles. So tracking what is the pressure, what is the velocity, what is the temperature of a single particle will be very tough. Okay, so there will be for a unit volume there will be like millions of molecules. So tracking millions of molecules is very tough. So therefore, the Eulerian approach will give you so the average of these flow properties. Okay, so that's what. So if you take this flow through this channel, here whatever the flow variation it is there across this cross section will be studied. So this is the Eulerian approach. In the case of Lagrangian approach, so basically you will see the behavior of fluid particle. So at t is equal to 0 initial time, so what is its position, and with that position the tracking of these fluid particles will happen. So let's say this is the fluid particle, it is going from here, from here, from here. So this tracking will happen. Okay, and here you can see basically flow properties will depend on let's say pressure will depend on x, y, z and time. Okay, and so here in the case of this Lagrangian, you have this initial time and coordinates. It's very important. And here let's say what is this pressure of this molecule 1, so molecule 2, molecule 3, so these things you will be calculating. But in the case of Eulerian method, so we will be seeing the average, okay, average properties across this cross section, in the sense throughout this flow. Okay, what is the pressure at this section, so at this section, at this section, at this section, so these things will be seeing. But in the case of Lagrangian method, you will be seeing So what is the behavior of particle? Fine. Yeah. So basically, the governing equations are very important. Any fluid flow problem or heat transfer problem, if you consider, so governing equations will decide the flow phenomena. So this is the moment continuity equation, and this is the momentum equation, and this one is the energy equation. So when a fluid particle is moving from point one, let's say this one, to let's say point two, so these equations will actually govern the fluid motion. Okay. So when a fluid particle is moving, it carries the mass, it has some momentum, so it has some energy. Okay. So as I discussed, you have two types of flow: incompressible and compressible flow. So in the case of incompressible flow, so if you don't have any temperature effects, let's say if you have any problem which is in you have a pipe and the water is moving from station 1 to station 2. So in this case, here if the temperature effects are negligible, since the water is incompressible fluid, so the temperature effects will be negligible. So in that case, so the energy equation will not be considered. So the continuity equation and momentum equation will be enough. Okay. So basically, depending upon the fluid flow problem, the governing equations will be considered. So if you have any heat transfer phenomena, let's say you have a jar, so you have a induction here, so here you have water in the jar. So when you heat this one, what happens? So you have the fumes coming, so you have the energy interaction inside this. So therefore in this type of problem, so you need this energy equation. So basically here, depending upon the fluid flow problem, the governing equations will be considered. So if you have only incompressible flow, where there is no change of temperature effects, or where there is no change of temperature and temperature effects, if they are not that predominant, so then the continuity equation and momentum equation would be enough to calculate these flow properties. So if the flow is incompressible, then this term will be also zero, so the density term also will be negligible. So if the flow is incompressible, then the variables will be, for a simple problem, pressure and velocity. So since the velocity is a vector, so you have u velocity, v velocity, and w velocity. Okay. So apart from this, if you have the flow to be compressible, and if the temperature effects are predominant, then you have temperature, then you have density, okay, you have enthalpy, so on, depending upon your physics of the problem. Okay. So here if you see that these equations will be used to model any flow problem. So it can be applied for any engineering problem. So flow over a car, flow through a pipe, flow over a building, flow over an aircraft. So internal flow, external flow, or biomedical kind of thing. Okay. So these things are there. Fine. Yeah. So whatever the governing equations, those are present here. So these will be applied to this model. Okay. So here, this is the domain where you will be evaluating the flow problem. Okay. So here, let's say this is the car. Okay. So let's say the flow is coming from this direction. Fine. So from this direction, it is going to this direction. Okay. So you will apply the initial velocity of the fluid, let's say 3 meter per second. So what is the pressure, and outlet condition, let's say what is the outlet pressure. Fine. So you will apply boundary conditions. These are like wall. Okay. This is as wall, and you will simulate the flow problem. Okay. Yeah. So basically, there are different types of flow in the CFD problem. So one would be internal flow, other would be external flow. So here we are seeing internal flow. So basically, in the case of internal flow, you can see that. So here, this is the problem of mixer. So when you take inside our home, like you will have mixes. So where you will put ingredients to mix up. Okay. So those blades, when it is rotating, so how these particles are rotating, okay, those things you can see here, visualize. So this is one kind of internal flow problem. So in order to build this, so let's say this domain you have, so these whatever the mixer length and height and the diameter, so those things you have to first decide it. Then you need to inside design the blade dimensions, design the blade with its dimensions, and then you need to give appropriate boundary conditions to rotate this model. Okay. So here you can see that the different, so when you perform this mixer, what happens, whatever the due to this centrifugal force, you can see that particles will be moving away from this center. So this is what happening here. Okay. So here you can also observe that the for the case of internal flow, there there is no need of putting extra domain outside this jar. Let's say this is the boundary where you are interested to see the flow. Okay. So outside the boundary, there is no attention required. Okay. So there is no requirement of attention for the flow phenomena. So here in this case, if the flow is internal flow, so whatever the physics that you need to study will be confined inside this domain. Okay, for the case of internal flow. Fine. So here you can see the external flow. So in the case of external flow, so here the wind turbine is rotating. Wind turbine is rotating with certain RPM. So here flow is coming in this direction. Okay. So in this case, the domain, so where you construct, so that would be very big. Okay. So domain in the sense, it is a region where you need to place the model to be investigated. So here, let's say this is wind turbine is our domain. So we have placed it at the center of the domain. So you will be sending the air from the inlet portion. Let's say this is inlet. Okay. And this is outlet. Okay. So this is inlet and this is outlet. Fine. So here you will apply some boundary conditions and initial conditions in the sense. So what is this boundary? Here inflow. Okay. This is outflow. So these kind of things. So what would be the initial velocity? Okay. So with what velocity the air is coming on the turbine? Okay. With what RPM the blade is rotating? Okay. So when this blade is rotating with this RPM, if the flow is, let's say it is rotating with RPM of 10 radians per second, let's say, for example, if this is coming around 4 to 5 meter per second. So when these two, okay, so you can translate. So V is equal to R omega. So here your R is nothing but the radius from this up to this thing. This is R. So omega is nothing but your 10 radians per second. So you can calculate the linear velocity from the relation of V is equal to R omega. Then you can see when this is coming. So the free stream velocity, when it is interacting with the linear velocity of the turbine, there would be change of the velocity. So these effects can be seen, okay, using this CFD. Fine. So basically here the domain, when you are investigating for the external flow, if you have the speed very less than speed of sound, then your domain should be very large. Why? Because so what happens, so when you have this is an obstacle when the air is going from station 1 to station 2, let's say. So air is moving in an open land. So in that open land, when you have installed wind turbine, so what happens, air will be flowing on this wind turbine. So it will the wind turbine will deviate the air. Okay, so it will act some force, and air also will act force on wind turbine. So therefore what happens, the disturbance disturbance propagated before the wind turbine, after the wind turbine, will be prolonged to very high lengths. Okay, so in this direction, and in this direction, in this direction, and in this direction. So the disturbance is propagated in all the directions, and to a large extent. So therefore, in the case of this low speed flow, so let's say if the speed is less than speed of sound, so your domain for the external flow, it should be large to capture the effects of the disturbance propagated in all the directions, to see what happens actually. Okay, this is very, very important. Yeah. So finally, once, so whatever we had seen is like, first we had seen what are the uh, types of the methods. One is like Eulerian, and other one is like Lagrangian. So out of these two, so Eulerian method will be used for the general problems. Okay, so if you go for any biomedical application, any nano material, like nano flow problems, so then the Lagrangian method will be applied. Why? Because in the case of, let's say, you have some microorganisms, so it is moving like from this station to other station, so these particles will be of very less in size, and the amount of particles present here would be very less compared to, so when you take a room, and when you take the air inside the room, okay, you have more number of molecules here, you have less number of molecules here. So in this case, so what happens, the Lagrangian method would be advantageous to find the flow properties. And in the case of when you have the large properties, so basically here you can say microscopic view. Okay, this is macroscopic view. Okay, so in the case of macroscopic, like the Eulerian method will be applied, but in the case of microscopic, this Lagrangian method will be applied. Fine. So but basically for a practical example, let's say, so this is the surface of the earth. Okay, so earth have different layers. So from here, if you are going to outer space, so what happens, so let's say this is the space. So here, this is the surface of the earth. So the density of the air here is 1.225 kg per meter cube. Okay, so but as you increase the height, the density of the air will be decreased. So here, let's say at 100 kilometer above the earth's surface, so the density would be approximately like e power 1 into e power like 3, or might be 4, okay, kg per meter cube. Okay, or it would be any other value, it's an approximate value. So will be very less. So density, if it is less, what is the meaning? So amount of molecules present per kg, sorry, the amount of molecules present in the meter cube length volume, so would be very less. Okay, if the molecules are very, very less, then this Eulerian approach is not that advisable. So you can use the Lagrangian to investigate. And whatever the governing equations are there, continuity, momentum, and these Navier-Stokes equations, so those will be applicable in the case of continuum. But if you are going for above Earth surface where you have space, so this is called rarefied flow. Okay, so in this case, the fluid particles are not closely packed; they are far away. So in this phenomena, like you can apply this Lagrangian method. Fine. So once you decide the fluid problem, then this will be first thing in CFD approach. So first you have to decide what is the fluid problem. then you need to go fluid. So the fluid mechanics will decide, so what is the physics of this fluid. So basically fluid problem in the sense, so flow over a turbine or flow through a pipe, okay, flow through any cylinder, okay, these things. So once you decide the fluid problem, so this fluid mechanics will decide what is the physics of this fluid. Then after, whatever the governing equations which are present, the mathematics will decide. So as I have shown you, so you have continuity equation, you have momentum equation, so you have energy equation. So based on the physics of the fluid, so if the heat transfer or if the temperature effects are predominant, then you need to have consider mass, momentum, and energy, three. So if you don't consider, then these two would be enough. Okay, so those equations would be in partial differential equation. Okay, those are partial differential equations. So you will so partial differential equations are, let's say you have this continuity equation, du by dx plus dv by dy is equal to 0. This is like 2D incompressible continuity equation. So these partial differential equations need to be uh, discretized, in the sense you need to form an algebraic or linear form to solve these equations. So with the help of numerical methods, you will actually linearize these equations. For whom you will linearize? For a given geometry. So whatever the domain that I have shown in the previous slides, in those things. Okay, so when you perform, so the next topic would be our thing is grid. So basically you will have a domain. So in the domain you will divide this domain into subdomains. So in these subdomains you will calculate the pressure, temperature, velocity of this fluid at these points. So these are grid points. Okay, so we will see these things again in the next session. So in order to perform these grid things, so you like you should require a particular domain. Then after you will use this appropriate programming language or any software to perform this analysis. Okay, so computer program code. So you have number of softwares. So you have ANSYS Fluent, you have OpenFOAM, you have CFD++. Okay, so many other softwares are there. So here those softwares at the background, they'll be running this programming code. Programming code is nothing but, so basically whatever the governing equations are present, continuity, momentum, and energy, those equations which are discretized, so with appropriate boundary conditions, will be solved with the help of matrix terminology. Okay, once the simulation is done, so you need to post process it. So post process the results, then you will get the results. Okay, so these are like major steps involved in the computational aerodynamics. So basically here in the case of fluid, if it is like water, then you can take it as a fluid. Then if you consider it as air, it can be termed as computational aerodynamics. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.